We're now going to look at a tool called the power spectrum. The power spectrum is a way of analysing a complicated waveform to look at the contribution from all the individual harmonics in that particular waveform. As a bit of background, we spoke about the Fourier analysis, which gives us the range of frequencies included in a given signal. If we just show an image of superimposed standing waves, we don't end up with a helpful result, we just see an absolute mess. So we need an alternate representation to infer any meaning in this particular representation. And we call this term the power spectrum. Fundamentally, what a power spectrum does is it looks at the power delivered by each of the harmonic components. This is proportional to the square of the amplitude. So if we have each of these components, anything with a high amplitude, we would expect to be delivering more power to that final result. And this power spectral density, c squared, is given by the Fourier coefficients. So we do this by looking at the Fourier coefficients A and B for each of the harmonic waves contributing to the final waveform, and we find the power contribution for each of those. So we have the power spectral density C as the sum of the square of each of the Fourier coefficients. Quite often we just use the spectral density C by square rooting the sum of the squares of the Fourier coefficients. And this gives us a way that we can readily compare the contribution from each of the components in that Fourier series. So the power spectrum fundamentally tells us the distribution of power in each harmonic. To go back to the square wave, we can see that some harmonics deliver much more power than other harmonics. When we look at the square wave in particular, most of the power is in the lower harmonics. So it's the lower harmonics that effectively rough out the main shape of that spectrum. So much of the structure coming from those lower frequencies, which means they're the ones delivering most of the power. When we get up to the higher frequencies, what we're doing is we're adding detail, or at least we're starting to square off that wave more and more by adding the higher and higher frequencies. So, as we say, most of the power delivered by the low frequencies in the square wave form. When looking at standing waves, we've spoken about musical instruments quite a bit. If we think about different musical instruments, the wavelengths and frequencies can be the same. So all of these particular waveforms have the same frequency, so they're all playing the same note. But they all sound very different. And the reason for this is they are produced by different combinations of harmonic series. So we've got the top one, which is a purely sinusoidal wave. We have the middle one, which we've looked at already, and the bottom one, which is even more complex again. These are produced by different combinations of the harmonic series, and each of them have different Fourier coefficients within that harmonic series. What that means is that they sound very, very different. So the spectra that we have here, the top one is an example of a tuning fork, the middle one is an example of an oboe, the bottom one is an example of a clarinet. So very different waveforms that we see. The simplest way to consider a power spectrum is to look at examples. So when we consider the tuning fork, we have a purely sinusoidal wave, so 100% of the power is being contributed by a single frequency. And this at the bottom here is a power spectrum. It tells us which frequency is carrying the power. As we see, a single frequency is carrying all of the power. The important thing is that this is a relative intensity. It's not intended to be necessarily an absolute measure. When we look at the clarinet, we see that we have a whole range of different frequencies carrying the power. And indeed, we see some gaps. We see some frequencies which aren't carrying very much power at all. And all of this goes together to shape the voice of that instrument. If we look at the oboe, it is different again. So we see a difference in the distribution of power carried by each of the harmonic components of that waveform. In summary, power spectra is quite a simple idea, but what it does is it allows us to, at a glance, determine the amount of power in each harmonic, and it's derived from that Fourier series for that waveform. It shows the contribution from each harmonic towards building that function, and the power spectrum is fundamentally built from those Fourier coefficients, which allows us to determine the contributions of each component. In our next video, we'll look at Fourier transforms and how they can be applied to different functions.